In this video, I want to talk about melting point and boiling point trends. So hopefully you know what melting is. When you take a solid and you convert it to a liquid, that's melting. That's a definition of melting. And when you take a liquid and convert it into a gas, that's boiling. That's a definition of boiling. However, what exactly is going on? Well, a solid has this very organized lattice structure. However, if you add enough heat, you can disrupt these intermolecular interactions, essentially breaking these bonds, disorganizing the solid, converting it into a liquid. So melting always requires heat because you need to add heat to disrupt those very organized bonds. However, once you have a liquid, now you can add more heat. And if you add more heat, you can add enough heat to give enough kinetic energy to these compounds to allow them to evaporate, to vaporize, and that leads to boiling. So something really important to realize is melting and boiling always requires heat. That will always be true. There are no exceptions. However, also what will always be true is if melting this compound requires 100 joules per mole, then vaporizing the compound will require more joules per mole. It always requires more heat to boil compared to the amount of heat needed to melt. So melting a compound requires a certain amount of heat. Boiling it requires more heat. So what exactly happens when we take a solid and we melt it into a liquid? Well, initially the solid is very organized in this very organized lattice structure. And what forms this lattice structure is Coulombic interactions, where one compound has a positive charge and the other compound has a negative charge. So due to these Coulombic interactions, they attract, forming a very organized lattice structure. However, if we want to melt this solid into a liquid, we need to break these bonds. Because again, it's these bonds that make a very organized structure. So we need to break these bonds to create a more disorganized structure, which forms the liquid. So how exactly do we do that? Well, again, we have these attractive forces, these Coulombic interactions forming the solid, so we need to break those Coulombic interactions. How do we do that? Well, we add heat. For example, maybe this solid, we need to add 6 kilojoules per mole, and that's enough heat to break these bonds to essentially melt this solid into this liquid. However, what if we had another solid? And what if this solid was made out of compounds with very large positive charges and very large negative charges? Then we would have these extremely strong Coulombic interactions forming this very organized lattice. So in this situation, it would require a lot of heat to break these bonds to turn the solid into this liquid. So maybe with this solid, it requires 27 kilojoules per mole of heat to break these Coulombic interactions to melt the solid into this liquid. So the key point is, whenever you have a solid, you need to add heat to break these interactions to melt it into these liquids. However, the stronger the Coulombic interactions that form the solid, the more heat that is required to essentially break the interactions to melt the compound. And that will always be true. So again, the weaker the Coulombic interactions, the weaker the charges and the weaker the Coulombic interactions, the lower the boiling point and the less heat required to melt the compound. However, the stronger the Coulombic interactions, the stronger the charges, the higher the melting point, the more heat that's required to break these interactions and melt this compound. For example, we could have water where we have these partial charges, this partial positive charge and this partial negative charge. However, we could also have sodium chloride, which has these ionic interactions with a large positive charge and a large negative charge, with these stronger Coulombic interactions. So remember what we learned. The stronger the Coulombic interactions, the larger the positive and negative charge, the more heat that is required to break these interactions to melt this solid sodium chloride into liquid sodium chloride. However, water has relatively smaller positive and negative charges. It has relatively weaker Coulombic interactions, so there's less heat that is required to break these interactions to melt this solid ice into this liquid water. So again, solids have these organized crystalline structures, like ice has this organized crystalline structure. However, if we add enough heat, we can break those interactions, those intermolecular interactions, disorganizing this solid into this disorganized liquid water. So essentially, there's a hierarchy when it comes to the strength of these Coulombic interactions. For example, if we have a formal positive charge and a formal negative charge, that forms the strongest Coulombic interactions. Then comes partial charges. So if we have a partial positive charge and a partial negative charge, that forms weaker Coulombic interactions. And then if we have London dispersion forces, that forms the weakest Coulombic interactions. So these formal charges form ionic bonds, which form the strongest Coulombic interaction, so therefore have the highest melting point and requires the most energy to break these interactions. Then comes partial charges due to these dipole-dipole interactions. Then comes London dispersion forces due to temporary dipoles, which are the weakest Coulombic interactions, so therefore have the lowest melting points. So compounds that have London dispersion forces require the least amount of heat to melt them. So we already explained how formal charges allow for ionic interactions, which is the strongest type of Coulombic interaction. For example, when we have sodium chloride, the sodium chloride salt, we know the sodium has a formal charge of +1. So therefore the sodium has a very large positive charge. And chloride has a formal charge of -1. So this chloride has a very large negative charge. So these two formal charges form very strong Coulombic interactions. So when we have formal charges forming Coulombic interactions, we call that an ionic bond. For example, we could also have the salt bridge. For example, this nitrogen has a formal charge of +1. This oxygen has a formal charge of -1. So we have these formal charges, so this forms an ionic interaction. So this forms a very strong bond. So therefore, it would require a lot of heat to break these interactions. These compounds would have very high melting points. But you might wonder, what exactly is a formal charge? What does it mean that this sodium has a formal charge of +1, while this chloride has a formal charge of -1? What exactly is going on? What is a formal charge? Well, a formal charge, whenever a compound has a formal charge, it means it has an unbalanced number of protons to electrons. For example, this sodium has a formal charge of +1, so it has positive charge density. Why? Well, this particular sodium has 11 positively charged protons and 10 negatively charged electrons. So therefore, there's one more positively charged proton relative to negatively charged electrons. So therefore, there's a net positive charge. That's why we have a formal charge of +1. However, why does this chloride have a formal charge of -1? Well, again, there's an unbalance of positively charged protons and negatively charged electrons. For example, this chloride has 17 positively charged protons and 18 negatively charged electrons. So we have one more negatively charged electron relative to positively charged protons. So we have a net formal charge of -1, a net charge of -1. So that's why we have a very strong positive charge on the sodium and a very strong negative charge on the chloride. And that's the basis of this ionic interaction, which forms very strong Coulombic interactions. So let's try another example. Let's say we have this water molecule. Something important to realize is that oxygen has a very high electronegativity, while hydrogen has a very low electronegativity. So what happens when we have a covalent bond between an atom with a high electronegativity and an atom with a low electronegativity? Well, we know electronegative atoms strongly pull negatively charged electrons towards them. So therefore, because oxygen is so much more electronegative than hydrogen, this oxygen is going to strongly pull negative charged electrons towards it. It's going to hog all the negative charge density. So because this oxygen is pulling negative charge density towards it, the oxygen is going to have a partial negative charge. And because it was pulling negative charge density towards it, the hydrogen is going to lose negative charge, so it's going to have a partial positive charge, which makes sense. If this hydrogen is losing negatively charged electrons, it's going to have a partial positive charge. So now what happens if we have two water molecules near each other? Well, we know the oxygen in water has a partial negative charge, and the hydrogen in water has a partial positive charge. So that's going to form a Coulombic interaction. So this will form what chemists refer to as dipole-dipole interactions. Here's one dipole, and here's another dipole. So again, because this oxygen has a partial negative charge and this hydrogen has a partial positive charge, we're going to form Coulombic interactions. And it's these attractive Coulombic interactions that form ice. Essentially, ice is just a bunch of water molecules forming these Coulombic interactions, forming a very organized lattice structure, forming a solid ice. So again, it's these partial charges that hold together an ice solid. And therefore, if we want to melt this ice, we're going to have to apply heat. We're going to have to apply heat to disrupt these attractive Coulombic interactions. Another example is this compound. So here we have a chlorine with a covalent bond to this carbon. So again, chlorine is more electronegative than carbon. So therefore, because chlorine is more electronegative, it's going to pull negative charge density towards it. So as it pulls negative charge density towards it, it's going to have a partial negative charge, and this carbon's going to have a partial positive charge because, again, it's losing negative charge density. So this will form a dipole. This will form a dipole. So now if we have another one of these compounds, we can form one of these partial charge interactions. Again, remember, the carbon has a partial positive charge and the chlorine has a partial negative charge, so they'll form attractive Coulombic interactions, and the same with these interactions. So again, this is another dipole-dipole interaction. So therefore, if we want to melt this solid, we would have to apply heat to disrupt these Coulombic interactions. However, what's important to realize is there's a special type of dipole-dipole interaction called hydrogen bonds. So all these atoms are extremely electronegative. So it doesn't matter what atom they're bonded to, they're going to pull negative charge density towards them. So they're all going to have very high partial negative charges. And also what's important to realize is if we have hydrogens bonded to these very electronegative atoms, every single time the electronegative atom is going to win. For example, in this bond, we know fluorine's super electronegative, so it's going to strongly pull negative charge density towards it, and it's going to win all that negative charge density. So it's going to have a very partial negative charge, so the hydrogen's going to have a very, very partial positive charge. So the same thing with these two hydrogens. They're bonded to these very electronegative atoms, so they're going to lose negative charge density, and they're going to all have partial positive charges. So we can form hydrogen bonds between these hydrogen donors and these hydrogen acceptors. So whenever we have interactions between any of these donors and acceptors, we form a hydrogen bond. For example, between these two compounds, between these two compounds, between these two compounds, between these two compounds, you can think of any combination, we form a hydrogen bond. So these are very strong partial charges. These are all very strong partial negative charges, and these are all very strong partial positive charges. So they're going to form very strong interactions. Any of these combinations of hydrogen bonds are going to form very strong dipole-dipole interactions. So these hydrogen bonds are the strongest type of dipole-dipole interaction. So these dipole-dipole interactions will be stronger than these dipole-dipole interactions. Because again, this is a hydrogen bond. This is one of those combinations. So this forms hydrogen bonds. That's a very strong dipole-dipole interaction. However, these are not dipole-dipole interactions. These interactions are not any of these interactions. So these are all dipole-dipole interactions. However, these are special dipole-dipole interactions, hydrogen bonds, which will be stronger than non-hydrogen bonds. So let's try one last example. So if we have these two hydrocarbons, they don't have any formal charges and they don't have any strong partial charges. So there aren't any real Coulombic interactions. But something important to realize is that all molecules have electrons. All molecules have electrons in these bonds. So they're all going to have some negative charge electron density. But also what's important to realize is there's going to be stochastic fluctuation in charge. For example, just by chance, just randomly, there's a chance that one region will become relatively strong in negative charge density, just with random fluctuation of electron charge density. So once this region has a partial negative charge density, it's going to induce a partial positive charge density in this compound. So again, there was just a random fluctuation where we had relatively high negative charge density here, which will induce partial positive charge density. So this can form an interaction, a London dispersion interaction. So again, we can have random fluctuation of charge forming these London dispersion forces, these interactions, these Coulombic interactions. But these are extremely weak interactions because again, here are partial charges where this oxygen will always have a partial negative charge and this hydrogen will always have a partial positive charge. So these are real partial charges which form pretty strong Coulombic interactions. These are temporary fluctuation in charges. So we're going to very briefly and temporarily have a very small negative charge, which will create a very small positive charge, which will create this very weak London dispersion interaction, this London dispersion force, this random fluctuation in charge, creating a Coulombic interaction. But something important to realize is the more surface area and the surface-to-surface contact, the stronger the London dispersion forces. For example, what if we have these two alkyl groups? Again, there's no real formal charges or partial charges. However, they have electrons. All molecules have electrons, so they're going to have random fluctuation in charge. We're going to have a random fluctuation of low electron density, creating a partial positive charge, which will induce a partial negative charge region, having this temporary fluctuation in charge, creating a temporary Coulombic interaction. But it's going to be a very weak Coulombic interaction. And due to the geometry and the structure of this compound, there's going to be very little surface area contact. So, yeah, we may form temporary London dispersion forces, but we're going to form very weak ones because there's very little surface-to-surface contact and interaction. While this compound has more surface area contact interaction, so this compound can form relatively stronger London dispersion forces. So again, both of these compounds are going to form London dispersion forces, which form these attractive forces that form these solids. But again, even within London dispersion forces, there's a hierarchy where this compound has stronger London dispersion forces than this compound. So therefore, this compound is going to have a higher melting point than this compound. But overall, this is the hierarchy, where again, formal charges, these formal charges that form these ionic interactions, these are the strongest Coulombic interactions. So they're going to require the most heat to break these interactions and to melt these compounds. Next comes these partial charges, which form these dipole-dipole interactions. These are the next strongest Coulombic interactions, where again, hydrogen bonds are stronger than non-hydrogen bonds. And then the weakest Coulombic interactions are these London dispersion forces, where again, the more surface area, the stronger the London dispersion forces, the higher the melting point, the more heat that's required to melt these interactions, these Coulombic interactions. So again, the point is there's a hierarchy. There we have this hierarchy. And again, the stronger the Coulombic interactions, the higher the melting point and the more heat that is required to melt the compounds. So again, these formal charges that form the ionic interactions, these are the strongest Coulombic interactions, so they require the most heat to break these interactions, so therefore they're going to have the highest melting point. Then comes hydrogen bond interactions, then come dipole-dipole, then come London dispersion forces. So again, as the Coulombic interactions increase, the melting and boiling point increases. And something important to realize is if this compound has a higher melting point than this compound, therefore this compound will have a higher boiling point than this compound. And that will always be true. If this solid has a higher melting point than this solid, then this liquid will have a higher boiling point than this liquid. That will always be true. As melting point increases, boiling point increases. For example, here are a couple theoretical melting points. But again, we can see as the Coulombic interactions increase, the melting points increase. These melting points increase. And again, as the Coulombic interactions increase, the boiling points increase for these theoretical liquids. So again, these are the types of intermolecular interactions that form these Coulombic interactions that form solids and liquids. However, what's also important to realize is we can have cross-mingling of these Coulombic interactions. For example, let's say we have this sodium with this formal charge of +1 and this oxygen with this partial charge of -1. We can form a Coulombic interaction, this ion-dipole interaction. Also, let's imagine we have the sodium with this formal charge of +1. It can induce a temporary negative charge. So this would be an ion-induced dipole interaction. And also we can have this chlorine with this partial charge of this partial negative charge induce a partial positive charge. So this would be a dipole induced dipole. So again, although I focused on formal charges forming interactions and partial charges forming interactions, we can cross mingle and have these diverse type of Coulombic interactions. But again, we'll still have that same hierarchy. A formal charge with a partial charge will have a stronger Coulombic interactions than a partial charge with an induced dipole. So again, these are the melting and boiling point trends.